Okay, so hi everyone. Thank you all for being here to a new Cosmo seminar. Today I'm thrilled to introduce you to Patricia Diego-Palazuelos from Instituto de Física de Cantabria. A little background about Patricia. She obtained her bachelor in physics and master in particle physics and cosmology at the University of Cantabria in the city of Santander. Now she is doing her PhD at the Observational Cosmology and Instrumentation Group at the Instituto de Física de Cantabria. Patricia is interested in the analysis of CMB polarization data. These days, she's working mostly on cosmic birefringence, but she has also dabbled in the study of the weak gravitational lensing of the CMB and extragalactic source detection in CMB physics, in CMB maps, sorry. Today she's presenting about cosmic birefringence, searching for parity-violating physics with the CMB polarization. So thank you, Patricia, for accepting our invitation, and please feel free to start your talk when you're ready.
Okay, so hello everyone, and first of all, I wanted to thank Gabriel for inviting me to be here today, even though it's just virtually. And after this very nice presentation, just before starting the talk proper, the only other thing I wanted to mention is that this talk is based on a series of works that is starting in 2019 with the original presentation of the methodology by Yuto Minami and collaborators, and that is very much ongoing. Just 1 or 2 weeks ago, Johannes Eskil and Ichiro Komatsu published a new analysis, a joint analysis of Planck and WMAP data. And I myself will soon publish a more methodological paper going into the technical details of the methodology and also the detailed study we did on the impact of systematics. And having said that, to start the talk proper, I have here one of these beautiful diagrams that summarizes the standard cosmological model that we also call the CDM, and is our current understanding of the universe. We believe that everything started with an inflationary period of accelerated expansion, where the quantum fluctuations were stretched out to form the very subtle overdensities around which dark matter and later on ordinary matter collapsed to form the large scale structure that we see today in the universe. And in this diagram of cosmic history, the CMB occupies a very privileged position. It is emitted around here in the epoch of recombination, when ordinary matter and light decouple. And it offers us a glimpse into these initial fluctuations and the conditions of the very early universe, when everything was still linear and easy to describe. And it also acts as a sort of backlight, illuminating everything that came afterwards and letting us gather information about that. And this is essentially why cosmologists have been using CMB temperature and polarization anisotropies in the past decades to gain information about a wide range of topics, from learning about inflation to mapping the distribution of dark matter in the universe through the weak gravitational lensing effect, to even constraining neutrino masses and the abundance of other light relics. And in this sense, I'm sure it's the same in Chile, but in Spain we have a lot of sayings of popular wisdom. And there's one in particular that reflects this kind of situation that my supervisor likes a lot. And in Spanish it will say something as el fondo cósmico de microondas es como el cerdo, se aprovechan hasta los andares, which in English will translate to something as with pork, we'll see even its throat. Meaning that cosmologists, we are extracting every last piece of information from every last CMB photon. And I couldn't resist to make this analogy, so today we will be taking something from, let's say, around here, and use CMB polarization to search for parity-violating physics in the universe. But first of all, let me just review the terms that we are going to use to describe polarization. In general, linearly polarized light traveling along the z direction can be described through the Stokes parameters I, Q, and U. We have that I will describe the total intensity, and Q and U, their combination, will describe the polarization intensity and the direction of the polarization state. And this is actually how CMB instruments measure polarization, we have a pair of polarization sensitive detectors, one in the direction of Stokes Q and another one rotated 45 degrees to measure in the direction of Stokes U. And the only inconvenience of these parameters to describe polarization is that they depend on the coordinate system that you choose. Depending on the exact orientation of your detector, your Q and U measurements will be one or another. And easy way that we can avoid this dependence on the coordinate system is to use essentially Helmholtz theorem, right? Helmholtz theorem tells us that vector fields can be described in terms of a curl-free component and a divergence-free component. We have that Q and U define a vector field, so we can decompose it into its gradient component or E mode and its B mode component, which is the curl component. And we call them E and B because this decomposition is completely analogous to the one classically done in electromagnetism, where you have the electromagnetic field and you decompose it into the electric field and the magnetic field. But the property of the C and B modes that is going to interest us today is the fact that they are also eigenstate of parity. They are parity-defined states. E modes are parity even and B modes are parity odd. And that means that when we describe CMB polarization in terms of its spherical harmonic coefficients, which are these ELM and BLM coefficients here, this is just the decomposition in spherical harmonics, and we calculate its correlation, which is what I am doing here. This is just a 2-point correlation function written in terms of spherical harmonics. Then I am going to get 3 sets of angular power spectra. 2 of them are going to be parity even, EE and BB correlations. And then we have a parity odd EB correlation. But the thing is that in lambda CDM, we believe that the universe has no preferred direction. And that means that the statistics of CMB anisotropies have to be invariant under parity transformations. So we actually expect no EB correlation to be produced in recombination. And in that way, if we actually find some in CMB observation, then that would be evidence of parity-violating physics, something that so far in the standard cosmological model and the standard model of particle physics has only been observed in the weak interaction. There are several beyond the standard model theories that predict such parity-violating physics. For example, we have some dark matter and dark energy models, in particular action-like particles, that introduce a new parity-violating pseudo-scalar field that, if coupled to electromagnetism through a Chern-Simons interaction, then it can make the phase velocities of the right-handed and left-handed helicity states of photons differ. And that has the consequence of rotating the plane of linear polarization clockwise in the sky, but this beta angle that depends on the time evolution of the pseudo-scalar field and its coupling constant with photons. And this rotation of the plane of polarization is what we usually call cosmic birefringence, because it is as if space itself was behaving like a birefringent crystal. Just the propagation of light through empty space can rotate its polarization state. In addition to axions, there will be other processes that could also produce this type of rotation. For example, Faraday rotation from primordial magnetic fields, that in this case will give us a rotation which is inversely proportional to the photon frequency squared. There are also some superluminal Lorentz violating electrodynamics that appears from a non-vanishing Veil tensor and will give us a rotation that is linear with the photon frequency, and even some quantum gravity models that can modify the dispersion relation of photons and will give us a rotation that goes quadratically with the photon frequency. Okay, but just to start, let's focus on the simplest case possible, where we have a birefringence angle that is independent of the frequency and is isotropic in space. In that scenario, we know that the polarization signal we observe, the observed E and B spherical harmonics, are going to be a rotation by this beta angle of the original CMB radiation, right? And in that case, the EB correlation that we are going to observe is no longer 0, but instead a rotation of the original angular power spectra of the CMB. And since the EE angular power spectra of the CMB is several orders of magnitude higher than that of BB, then essentially if we find anything that resembles the EE angular power spectra in the observed BB correlation, then we could attribute that to birefringence. With a bit of algebra, we can generalize a bit more this expression so that we have that the observed BB correlation is a rotation now of the observed EE and BB angular power spectra, so that we don't need to assume a theoretical model for the CMB angular power spectra. And this very, very simple equation right here has been the base of most of the harmonic space methodologies applied in the past to measure birefringence. For example, a popular one is the so-called estimator that just tries to find the zeros in this equation, but by minimizing a chi-square. And these types of searches have been applied to quite a lot of datasets in the past. We have, for example, measurements here even from Planck in 2015. And as you can see, these measurements have been gotten quite good. We have uncertainties that are getting quite low over the years. So the question is, why has no one claimed a detection of cosmic birefringence? And the answer, as it's becoming more and more evident in this epoch of precision cosmology that we live in, is systematics. It doesn't matter how good your statistical uncertainty is, you also need to have a very tight control of systematics if you want to do a precision measurement like the one we're trying to do here. And in particular, there is a type of systematics that is especially pernicious for this type of analysis, and that is the miscalibration of the polarization angle of the detector. As we said a couple of minutes ago, CMB detectors have one detector in the direction of Stokes U and one detector in the direction of Stokes U. And we need to know very precisely the orientation of both of them, because any small alpha miscalibration is going to produce a rotation of the observed polarized signal that is completely degenerate with that of birefringence. Meaning that when we look at the observed BB correlation, we are going to measure beta plus alpha instead of just beta. And in addition to that, we also have other type of systematics like intensity to polarization leakage, beam leakage, or cross polarization effects that can also produce spurious TB and EB correlation that will confuse our measurement of birefringence. And once you realize that, if you don't take any special precautions, you see that what we have been measuring to such very good statistical uncertainties is actually alpha plus beta. And if you do your homework and try to incorporate your knowledge on the calibration of the instrument and all of your known systematics, which is not always easy to do, you can see that the systematic uncertainties that come from that have often been the limiting factor in this type of analysis. And that happens because for these datasets, the precision in the calibration of polarization angles has been between 0.5 and 1 degree, which is pretty high for the type of precision measurement we want to do. And of course, this is going to improve in the future, but it's the limiting factor for analyzing these already available datasets. But in when was it? In 2019, Yuto Minami, Echiro Komatsu, and collaborators came up with a clever way to bypass this limitation imposed by calibration. And if you remember this diagram from before, we're actually here at the very end inside the Virgo cluster, inside the Milky Way, and putting satellite and putting instruments to measure the CMB somewhere around here in satellites in L2 or directly in the surface of the Earth. And that means that every time we look up to try to measure the CMB, the first thing we actually encounter is our own galaxy, which happens to be a very bright emitter in polarized microwave radiation. It's mainly synchrotron radiation at the lower frequencies and thermal dust are highest ones. And the key point is that for all of the processes that we mentioned before, the amplitude of the birefringence radiation always depends on the propagation length of photons. So it is safe to assume that the photons that were emitted by our galaxy right next to us, that the birefringence seen by the photons that were emitted by our galaxy right next to us is going to be negligible when compared to that seen by the CMB photons that have been traveling all the way back from recombination. So we will have galactic foregrounds negligibly affected by birefringence, but they cannot escape the miscalibration of the detector. So if we take a step back and work with frequency maps instead of clean CMB maps, we can use foregrounds as our calibrator. And that is precisely what we're going to do, right? We have to add foregrounds to our observed signal, with them being only rotated by alpha, unlike the CMB that is rotated by both angles. And with that, our model for the observed PV has the same term as before, and two additional ones. One that depends on the foreground intrinsic EV correlation, and one that is just a rotation of the CMB angular power spectra. Now, as it was initially done in previous works, we could in principle neglect this foreground EV correlation because according to current experimental constraints, this is still statistically compatible with being zero. But we'll get back to this in a minute. And from this model for the observed EV correlation, we can just build a Gaussian likelihood to simultaneously determine both angles using the information contained in the cross correlation of the different frequency bands of any given CMB experiments and a theoretical model for the CMB angular power spectra. And if you give me a second. Okay. Now, this is the methodology that we recently applied to the latest Planck data release, known as PR4 or MPIPE, which, to give a bit of context with respect to previous releases of Planck data, its improvement is that it offers a new reprocessing of raw and calibrated data from both the low and high frequency instruments of Planck, and it achieves a scale-dependent reduction of the total uncertainty due to the addition of the data acquired during repointing maneuvers, and also a general improvement in the modeling of noise and systematics. And we just took MPIPE 100, 143, 217, and 353 GHz data and cross-correlated the different AV detector splits to reduce the effect of noise and systematics. Now, AV detector splits are produced by taking all of the antennas observing at the same frequency and dividing them into independent subsets so that you have two independent measurements of the same thing, so their cross correlation cancels out noise and systematics. Problem is, since they are built from independent subsets, they can technically have slightly different miscalibrations. So we have to fit a different miscalibration angle for each of them. And that makes for a total of 8 miscalibration angles plus birefringence, then it's 9 free parameters. And as it was done in previous works, we also focus on high-L data to target the birefringence angle from recombination. And we started by considering a null foreground correlation. And a strong point of our analysis that I also wanted to mention is that we find consistent results across 4 independent pipelines operated by different people who use different pseudo-CL estimators and also have slightly different implementations. We have Johannes Eskil, Yuto Minami, and Mathieu Tristan that follow the original implementation and obtain the posterior distribution with Markov chain Monte Carlo methodologies. And I myself, I run an iterative algorithm that analytically minimizes the log likelihood to find the maximum likelihood solution, which, as you can imagine, makes for a much faster methodology ideal to for the analysis of many simulations. And to start with the results, first thing we did was just mask the brightest regions of CO of the CO. Yeah, sorry. We just mask the regions where the CO emission line is the brightest in the galactic plane and extragalactic point sources. And for this almost full sky configuration, we find a birefringence angle of 0.3 plus minus 0.11 degrees, which is consistent with, but more precise than previous measurements. For example, I have here as reference the one obtained by the Planck team in 2016, the one from the table we saw a minute ago. These birefringence and miscalibration angles that we're fitting are an isotropic rotation of the whole sky. So in principle, no matter what we look in the sky, we should find consistent values. And we thought that checking that this was indeed the case could be a good consistency test to start with. But as soon as we started masking the brightest regions of foreground emission in the galactic plane, we realized that our measurement of birefringence actually decreases, reaching even negative values when we mask about a 30% of the galactic plane. And it is not shown in the graph to not overcrowd it too much, but at the same time that beta is decreasing, alpha shows the complementary increase, so that the beta plus alpha sum remains constant and at about 0.3 degrees. And I'm sure you're asking yourselves, how is it that these supposedly isotropic angles seem to have a mass dependence, right? This shouldn't be possible. And the answer, as it happens to be a common occurrence in CMB analysis, is dust. We are using foregrounds, and in particular at these frequencies, thermal dust emission, as our calibrator. We constrain the miscalibration angles using dust, and dust is a very complex and very anisotropic signal. So what this drift is telling us is that there is indeed a dust-TV correlation that we were wrong to ignore, and that is highly mass dependent. Right, to see a bit better how foregrounds affect this analysis, we can take our model for the observed foreground EV correlation, and with a bit of algebra, rewrite it so that it is proportional to the sine of 4 times the miscalibration angle, plus 4 times this new effective angle, gamma sub L, which within the small angular approximation is just the quotient of the foreground EV over EE minus VV. And when you write things this way, you realize that if the foreground EV happens to be proportional to foreground EE minus VV, then this gamma sub L no longer depends on the multiple, it is a constant. And in that case, it is completely degenerate with alpha, meaning that we are actually measuring alpha plus gamma and beta minus gamma, with the alpha plus beta sum remaining unaffected, which starts to sound familiar, but we can go a step further because previous analysis on Planck data have already reported that dust has a positive TV correlation, which means that it's also plausible that dust can have a positive EV correlation. A positive EV will make for a positive gamma, and that produces a reduction on beta and an increase of alpha, just like the ones we see on our data, right? And a positive gamma also means that our measurement is actually a lower bound for the true value of birefringence. But this is not the end of the world. Since now that we know that this is a problem, we just need a model for the dust TV correlation so that we can include it in our equations, correct for it, and find an unbiased measurement for birefringence. We found a model for this in this work by Susan Clark, Brandon Hensley, and collaborators, where they demonstrate that dust TV correlation appears from the misalignment between the filamentary dust structures of the interstellar medium and the plane of sky orientation of the galactic magnetic field. If you have your dusty filaments perfectly aligned with the local magnetic field lines, we expect no TV or EV correlation. But as soon as you start to have a small misalignment between them, TV and EV correlation appear, with their sign depending on the actual angle of the misalignment. In particular, TV and EV are expected to be proportional to the sine of the misalignment angle, while TE will be proportional to the cosine. And in this work, they also come up with a relatively simple model to predict the sign and amplitude of dust TV by measuring E, TE, and TV. That with a small modifications, we just adopt their model. So that we take dust TV to be proportional to dust EE times the quotient of TV over TE. And we are going to obtain our power spectra for the dust from M5 data at 353 GHz, because that band is anyways dominated by dust. And we are also going to leave a free amplitude parameter H2L to fit alongside beta and alpha in the likelihood. And this correction leads us to these new black data points that, as you can see, are compatible with amongst each other for the different sky fractions within the error bars, of course. And more importantly, they are consistently positive, meaning that indeed a dust TV correlation was the reason for this decline that we saw before. And we also tried a completely independent approach to further confirm this. And this time we used the Commander Sky model. But to give a bit of context, a common procedure that we use in CMB analysis to obtain clean CMB maps from your observation is to assume that what you have in the sky is CMB plus some parametric model for each foreground component. And Commander is a Bayesian code that does precisely that. It takes as input Planck conservations at each frequency. It assumes that what we have in the sky is a CMB plus a parametric model of a power law for synchrotron and a parametric model of a one component modified black body for dust. And in return, it gives you a clean map of the CMB and templates for each foreground component. So we just took the dust template, calculated its angular power spectra, and introduced that into our equations, leaving also a free amplitude parameter to fit alongside beta and alpha in the likelihood. And with this other model, we get the purple triangles that, as you can see, are again consistently positive for all sky fractions, further confirming that the decline was produced by an unaccounted for dust TV correlation. And they are also in very good agreement with the filament model here at the smaller sky fractions, but we have a bit of attention here at the almost full sky result, which is not very worrisome in the sense that is only telling us that the Commander sky model might not be able to fully capture the complex structure of dust at the center of the galactic plane. And other caveats of this second approach is that Commander templates are not yet signal dominated for EV, and they are also derived from previous releases of Planck data, which means that they are obviously very well correlated with, previous releases of Planck data. So they are very well correlated with the M-pipe release, maybe even to the point of reproducing some of the noise and statistical fluctuations. So in a sense, we may be overfitting a bit, let's say, which reduces our covariance metrics and leads to slightly underestimated error bars, or can lead to slightly underestimated error bars. And the other caveat is that in this parametric model that Commander assumes, at no point they consider that different frequency bands may be affected by a different miscalibration angle. So the final template may have a spurious EV correlation produced by the average rotation of all the other frequencies. But we believe this effect to be small because the EV that we get from the template does not really resemble that of a rotation of EE. On the other hand, the filament model might be somehow limited in its simplicity. We don't know if it is able to capture correctly the complex interplay between dust and magnetic fields at all scales. So in that sense, both of them are complementary. And I started the talk going on about the importance of controlling and knowing your systematics, so I cannot end it without showing you how robust this methodology can be against systematics. And to do so, we did a very detailed study of the official M-pipe end-to-end simulations, which are produced by passing the expected CMB and foreground signal through the full Planck instrument model and the M-pipe processing pipeline to give frequency maps that contain both CMB and foregrounds, but also instrumental noise and all of the known systematics. And for these frequency maps, you can subtract the input foreground and CMB signal, and that gives you what they call residual maps, which contain just the noise and systematics. But thanks to this way they have been produced, they still capture all of the nonlinear responses and the coupling between signal and noise that the instrument and the processing pipeline can introduce. So they are very realistic end-to-end simulations. And since we believe we already understood the role that foregrounds play in this analysis, let me just show you the results we get when we analyze simulations of CMB, noise, and systematics. Only downside is that since I took away the foregrounds, I can no longer break the degeneracy between the alpha and beta angles. So I have to choose if I want to fit a different angle for each frequency, which will behave like a systematic miscalibration angle, or the same angle for frequency bands, which will behave like a systematic beta angle. No problem, we can take turns doing that. And these are the mean systematic angles that we find for the different analysis masks. Here, the data points are the average over 100 simulations, and the error bars are the simulation dispersion over the square root of n. So it's the error of the mean. And first thing I want to point out is that these systematic angles do not really change from one analysis mask to the other, meaning that none of the known systematics can produce the decline that we saw on beta as we enlarge the galactic mass, which further reinforces our interpretation that it is produced by foregrounds. And second of all, although I think it's the first thing you may have noticed, is that we are finding some very clear systematic angles here, especially at 100A and 100B detector splits. And I want to stress that although with the simulations, we can determine very precisely what is the value of these systematic angles. If we go to the data and try to find them, if you look at these statistical uncertainties that we have, we will only be able to detect them at a 2-point-something significance. So although they are here and we need to understand where they are coming from, they are only moderately worrisome. To do that and find where they were coming from, we took a closer look at the data. For example, I have here the EV angular power spectra coming from the simulations when you cross-correlate the 100A and 100B detector splits. And here the power spectra is the average over 100 simulations, and it's also being like within the data. So that's why it looks so smooth. And you can see that there is some spurious EV correlation that is for sure producing these systematic angles that we just saw. If you remember from the top of the talk, I named a couple of possible systematic instrumental systematic that could produce this type of spurious EV correlations. In general, intensity to polarization leakage will give us something that looks like DT. A cross-polarization effect will give us something that looks like EE, and a combination of both, something that looks like TE. And in addition to that, we can calculate the spurious EV correlation expected by beam leakage because we have the window matrices produced by the quick polar algorithm specifically for the beams of Planck. Right, so to pinpoint which one of these effects is the one producing these correlations, we just try to fit this angular power spectra from the simulations with this simple model. And I am showing you here the best fit for each of them. And you can already see it by eye, but if you want a more quantitative assessment, I also have the reduced chi-squares of each of them. And the best fit corresponds to the red line, which is a cross-polarization effect. And apart from having an actual alpha miscalibration, a cross-polarization effect is actually the worst kind of systematic we could have for this type of analysis because it is introducing in EV something that looks like a rotation of EE, and that is precisely what our estimator uses to determine rotation angles. To stress this point, I can overlay here this green region, which is the 1 sigma confidence contour of the EV correlation produced by the systematic angles we saw in the previous slide. And as you can see, it is perfectly tracing the red line. It is 100%, so the cross-polarization effect is 100% reason behind the systematic angles and these frequencies. And since it is a rotation of EE, that's why we can detect these angles here with such a high significance. But in addition to those, we also have some worrisome angles here at 143A, 143B, and 217A. Right, these ones at a much lower statistical significance, but still we repeated the same analysis as before to try and find out why are they present. And if you repeat the same kind of analysis, you find that the best fit in this time corresponds to a beam leakage effect. That is the blue line, right? And if you compare it with the red one, which will be the rotation of the EE spectra, you can see that they don't look very much alike. Okay, the angular dependence of both effects is quite different. So our estimator doesn't really have a tool to reproduce the angular dependence of beam leakage, but even so, it is trying to a moderate success, I will say. You can see how here the green contours are trying to accommodate this fluctuation relatively good, although here it's quite bad. But the estimator has some degree of freedom, some tools to try and accommodate this other systematic that is beam leakage. The reproduction is not perfect, and that's why we have these angles at a lower significance. And having said that, I want to remark that finding these systematic angles and understanding what is the systematic, the instrumental systematic causing them underneath, this actual values do not need to agree with the ones that we find in the data, because the simulations do not include, and in fact cannot include, the miscalibration present in the data. It is unknown. It is unknown, so we cannot think of it ahead of time. Instead, what this study is telling us is that even in the presence of such systematics, our methodology can correctly capture them into the alpha miscalibrations and leave our measurement of birefringence virtually unaffected by them. The systematic birefringence angle we are finding here is 0.009 degrees, which is completely negligible with the 0.11 degrees statistical uncertainty that we have in the fit to the data. And that is the reason why in this work we chose not to correct for any of these systematic effects. And just to leave you with a brief recap, I hope I have convinced you that this methodology allows for a systematic free measurement of birefringence that is compatible with previous measurements from Planck data, but greatly reduces the total uncertainty. But since we essentially use foregrounds as our calibrator, we are quite sensitive to the dust TV correlation. So in a way, we have relaxed the requirement on calibration, but now having a precise characterization of polarized foreground emission is the name of the game. And we have proposed two independent ways to model for dust TV, and all the results are promising, and the agreement between both models is very encouraging. This was just a first try, so at this step, we prefer to be cautious and don't assign any cosmological significance to our measurement of birefringence until we can improve our models for polarized foreground emission. And the very last thing I wanted to show you is this first follow-up work published by Johannes Eskild, where he added the low frequency channels of Planck, so 30, 44, and 70 gigahertz channels. And with that, he finds a birefringence angle of 0.33 plus minus 0.10 degrees for the nearly full sky analysis, which is not bad. It's a 10% reduction of the total uncertainty. But the most interesting part of this analysis, in my opinion, is the study he did in the frequency dependence of birefringence. Until now, we have been fitting the very same angle for all frequencies, and that will give you this green region here. But you can also fit independent birefringence angle for each frequency, which will give you these black data points, and even assume that what you have is a birefringence angle that behaves like a simple power law, for example, and that will give you this shaded green region. Shaded black region. The spectral index corresponding to the best fit is of minus 0.35, which is quite large error bars yet. So you can kind of still see here a frequency dependence. But if you repeat the fit, this time forcing the spectral index to take a fixed integer value and compare the chi-squares of the fits, you see that actually the data seems to favor having no frequency dependent, a null spectral index. And from all of the processes we talked about at the beginning of the talk, the one that is frequency dependent is actually Chern-Simons coupling to a light pseudoscalar fit. So we still have a lot of work to do. We have to keep bringing down the statistical uncertainty and also be completely sure that foregrounds are in no way biasing our results. But if confirmed, this signal could be attributed to an ultralight axion-like field and would be evidence of parity-violating physics outside the quick interaction, which is something very exciting and could have very profound implications for modern physics. And thank you. This is the end.
Thank you, Patricia. Thank you for your great talk. We have some time for questions. So if anyone has one, please go ahead. I see that Spiros has a question, so go ahead.
Yeah, thanks a lot for the nice talk. So if you have, for example, during inflation some spinning field, some vector or some tensor, let's say, that acquires some vacuum expectation value, would that also be a scenario where you would expect EB correlations or birefringence?
Yes, there are some models of, for example, chiral gravitational waves.
Exactly, yeah, for example.
Inflationary models that also predict inflation to be anisotropic, kind of patchy, and that can also produce an EB correlation, right?
And
so,
you know the frequency dependence of that, or?
No, I don't know the frequency dependent, but the thing is that these models, what give you is an intrinsic foreground EB correlation here. The CMB would be emitted already with that EB correlation. And we can just add this term right here. It will appear as a cosine of 4 times beta plus this other term. And the thing is that the angular dependence is different. Right? These other models would predict something that, I don't know, we have, I don't know the shape, but it would be different to that of EE. So even in the presence of these other models, we could still, if we have a model for the angular power spectra of that EB correlation, for sure, but even in the presence of that, we could still try to find something that is a rotation of EE. And that is why here I say that anything resembling EE could be attributed to birefringence. Right, the key point is that we know the angular dependence that this rotation should have. So we can accommodate also these other types of models. But yes, very good question.
Okay, any more questions? So here we have one.
So Patricia, I had a question. Probably you mentioned before, but so how do you take into consideration the foregrounds exactly, in the sense that you have sort of model and then you try to match for instance, the high frequencies mapped of Planck, or is it a different way? So how do you exactly use it?
Could you maybe repeat the question? I couldn't hear very well.
How do you take into consideration how you do your model, in particular, the foregrounds?
Okay. Yeah, so when we use the commander template, in this case, the modeling is very straightforward. Commander gives us a map for the dust and a way to scale it to different frequencies. So by using this, I have at each frequency my Planck observations and another map corresponding to what I expect the foregrounds to be, dust to be at that frequency. So I can calculate the angular power spectra of both maps, even correlate them, and put that into my equations. And for of course, here I would be trusting that the scaling laws of frequency dependence of commander are correct and the correct ones to scale those templates to different frequencies. And in the other model, it's kind of we modify our equations to have so that the terms involving foregrounds have this shape, and we calculate this gamma angle like this. So we change a bit the shape of the equation so that we now have this other additional angle, and we put the value of this angle like this, leaving only this free amplitude parameter.
So basically, okay, for the first one, for the commander, you rely on the CMB maps of the higher frequencies. Okay.
Yes.
And the question is, okay, the last result that you showed that beta does not, well, if you force the power not to be integer, like this one. So basically, this result is this, as you said, if it is confirmed. So basically means that dust does not do that much at the end, or am I wrong? I mean, says maybe I would think that dust does affect some frequencies rather than all the frequencies.
Yes, dust will be only important above 70 gigahertz, more or less. And actually including these lower frequencies can help you because synchrotron, which is the dominant foreground on these lower frequencies, doesn't have, according to current experimental constraints, doesn't have IV correlation. So having some foreground free, let's call it, frequencies in the sense of EV is helping you to get less biased results. And actually this, you see that here the value of beta for when you fit 353 gigahertz only is kind of lower, probably because here dust TV is not corrected very well, and that's why it's pushing it down. So even though we can mitigate those effects, if you try to fit something that is that depends on the frequency, that dust is still quite relevant. Yeah.
Thank you so much.
Any more questions? Go ahead.
Thanks, Patricia, for the nice talk. I see that in that plot you select a value for the fraction of the sky. Then do you have a preferred value for that, or that you trust more, or it doesn't matter much? Yeah. After you explain, of course, the previous issue about the fraction.
Yes. That's the most tricky question. Actually, here Johannes chose this to show the results only at this value because he's trying to fit a different birefringence angle to each frequency, and that is kind of pushing the methodology to the limit because here, if you remember these equations, the CMB is rotated by both angles. So if we made beta also depend on the frequency, we are trying to obtain from the same CMB observation, the measurement of alpha and the measurement of beta, which is quite difficult because the degeneracy between both angles is only partially broken. So if on top of that, you reduce the sky fraction and start to leave foregrounds out of the analysis, then you can no longer break the degeneracy and you will get something that is completely degenerate. So when you try to fit different birefringence angles for each frequency, you need to go to this almost full sky analysis if you want to be able to differentiate. And in general, I would say that almost full sky is better because you have more statistics and you can determine better the statistical uncertainty. And also is the case where you have more foregrounds, so you have more discerning power between miscalibration and birefringence. But the thing is that foregrounds are more difficult to model in this almost full sky case. And you see that is actually the only one where we have a bit of a disagreement. So ideally, the best case is the almost full sky analysis, but it is still the one that we potentially can find more troubles in. So it's a bit tricky right now.
Thank you.
Okay, any more questions? So I think if there are no further questions, let's thank again Patricia.
Again, thank you for having me.
And thank you everyone for coming today. Hope to see you again in the next seminar. Bye everyone. Bye Patricia.
Bye.